Okay, the AP Calculus course in review. Here's my formula sheet, and let's just take a look at it. Let's go through it as briefly as we possibly can here. Limits is one of the first topics that we looked at. A limit is simply a y value. I don't know if you could see this. Hopefully you have this printed out in front of you, but a limit is simply a y value. So there's different ways to figure out what that y value is. One of the ways you could do is just, or one of the things you could do is just plug in the value for x to determine the y coordinate. Another thing you could do is take a look at the graph. A lot of times you won't have a graphing calculator, so you'll need to make an XY table and figure out what's going on with the points, to sketch the graph. If you happen to plug in a value for x and you get a number divided by 0, that means that you have a vertical asymptote. Okay, so graphically, there would be a vertical asymptote. Only if you plug in and you get some number divided by 0. Okay, and when you have a vertical asymptote, that's going to mean one of three things. The particle's either going up to infinity, it's going down to negative infinity, or it's going to negative infinity on one side and positive infinity on the other. So the only three answers you can get once you establish you've got a vertical asymptote is if they asked what's the value of the limit as you come in from the left, that would be positive infinity. If they asked what's the value as you come in from the right, that would be negative infinity in this case. And if they asked in this case what's the value as you approach this vertical asymptote, I don't know, let's say that this is at x equals 2. What's the value of the limit as you approach this value of x equals 2 from both sides? Then that would be does not exist. All right, because the left-hand limit, which is going to infinity, doesn't equal the right-hand limit, which is going to negative infinity. Right? That doesn't always happen. Just because you have a vertical asymptote doesn't mean that you can't get something like this. It's going to infinity on the left and going to infinity on the right, so then the value of the limit would be positive infinity. Other ways to look at limits, you could factor and cancel common factors and then reevaluate the limit. You could do L'Hopital's rule. You can only do L'Hopital's rule when you plug in. Okay, so that's why this one's so important here. And you get 0 over 0 or infinity over infinity. Then and only then can you use L'Hopital's rule. What's L'Hopital's rule? Well, you take the derivative of the top fraction, or you take the derivative of the top part of the fraction, and then you take the derivative of the bottom part of the fraction. It's not the quotient rule. You just take the derivative of the top part by itself, and then you take the derivative of the bottom part by itself. You get a new function, and then you simply reevaluate the limit. And another way to evaluate limits is power battles. You're only going to use this when you're evaluating a limit when x approaches infinity or negative infinity, or both. So that's the only time you're going to use power battles, right? When you're looking at the end behavior. What happens at x equals a million? What happens at x equals negative 1 trillion? Obviously, exponents are going to dominate at that point, so that's why we do power battles. If the numerator wins the battle, if the numerator has the highest exponent, then that infinity, or I'm sorry, then that limit equals positive or negative infinity. You have to figure out which one it is by plugging in values, right? So you plug in, x equals 100, and maybe you get a million. If you get a million, then obviously it's going to infinity. If you plug in, x equals 100, and it's going, you get a y value of negative a million, then obviously your limit is going to negative infinity. So if the numerator wins, the value of the limit goes to plus or minus infinity. If the denominator wins, if the denominator has the highest exponent, then your limit equals 0 because that fraction is getting smaller and smaller and smaller. And if the powers or exponents are tied, then the value of the limit equals the coefficients. All right, so I just have a couple of quick examples here for you. This first one says, what's the value of the limit as x approaches 6? And we could do it from the left, we could do it from the right, or we could do it in general. Okay, so I made a little XY chart you see here. First thing I could do is I could plug in 6, but if I plug in 6, I get 8 over 0. So at least I know that I've got a vertical asymptote at that point. but I'm going to have to plug in some values near x equals 6 to figure out what's going on. When I plug in x equals 5, I get a negative 1. At that point, I can be positive since it's below the x-axis, that it's going down to negative infinity. It's going to stay below the x-axis. There's no way that it could turn around and cross the x-axis between 5 and 6 because there is no root of this equation that would equal 5.5. All right, and then when I plug in 7, a little bit to the right of x equals 6, I get a positive 1. Again, since there's no root for this equation or no x-intercept for this equation between 6 and 7, I can be positive that it will stay above the x-axis and go to positive infinity. So if they ask me what's the value of the limit as x approaches 6 from the left, it's going to negative infinity. If they ask me what's the value of the limit as x approaches 6 from the right, it's going to positive infinity. And if they ask me just in general, what's the value of the limit as x approaches 6, well, it does not exist because the left-hand limit does not equal the right-hand limit. Here's another example. This is the limit as x approaches 0 of x over the absolute value of x. Again, I could do this in 3 different ways. All right, so those are 3 different separate examples. But again, I could plug in 0, you get 0 over 0. That's called indeterminate form. It doesn't necessarily mean you've got a vertical asymptote because there's not a number other than 0 divided by 0. This is just 0 over 0. So if I do an XY chart to figure out what's going on graphically, at -2 I get -1. At -1 I get -1. At -0.5 I would still be at -1. Of course, there's no value at x equals 0, so I'll just put an open circle there. And then as we approach it from the right, if I plug in 3, 3 divided by the absolute value of 3 is 1. If I plug in 2, I get 1. If I plug in 1, I get 1. If I plug in a half, I get 1. If I plug in a quarter divided by the absolute value of a quarter is still 1. All right, so that's what it looks like graphically. And then I can answer these 3 questions. What's the value of the limit as x approaches 0 from the left? Well, that would be -1, right? Because we're at a y value. Remember, limits are y values. We've got a y value of -1. What's the limit of this function? There should really be an f of x in here. What's the limit of this function as x approaches 0 from the right? So if we come in from the right, we are approaching a y value of 1. We're at y equals 1. We're at y equals 1. We're still at y equals 1. So the value of our limit is y equals 1. A limit is a y value a function approaches. It doesn't have to get there. Of course, at x equals 0, it's not at y equals 1, but it's approaching y equals 1. And then if they asked us for the value of the limit as x approaches 0 in general from the left side or from the right side, of course this limit does not exist because the left-hand limit does not equal the right-hand limit. All right, so that's the quick story on limits. Continuity, let's talk about a function that is continuous. A function is continuous if the function exists at that point. So if we're trying to determine if a function is continuous at some x value, say x equals 5 or x equals c, the function needs to exist. There needs to be a point at that x value. There also needs to be a limit as x approaches c from both sides. So the limit has to exist. You can't have DNE for the answer to the limit. And the value of the function needs to equal the value of the limit in order for a function to be continuous. This is the technical definition of continuity, but in general, a function is going to be continuous if there are no holes, if there are no jumps, and if there are no vertical asymptotes. So if you've got a picture of the graph and you don't see any holes, any jumps, or any vertical asymptotes, then the function is going to be continuous. Differentiability is a little bit more stricter in terms of trying to achieve a function that's differentiable. The function could be continuous, right? But you might have a corner or a cusp or a vertical tangent. A vertical tangent, not a vertical asymptote, but a vertical tangent is when you try to find the slope of the function, and the slope of the function is undefined, right? Then you would have a vertical tangent. So in order for a function to be differentiable, there's 6 things that have to happen. You can't have any holes, you can't have any jumps, you can't have any vertical asymptotes. Those are the same 3 things for continuity. But also, you can't have any vertical tangents. That's this right here, right? The slope can't be undefined. You can't have any corners, and you can't have any cusps, right? Or else there's a gazillion tangent lines you could draw, and which is the slope? Well, we don't know. All right, so a function is continuous if you don't have any holes, jumps, or vertical asymptotes. A function is differentiable if you don't have any holes, jumps, vertical asymptotes, vertical tangents, corners, or cusps. All right, so 3 requirements for the function to be continuous and 6 for the function to be differentiable. Notice the technical definition for differentiability is the left-hand derivative needs to equal the right-hand derivative. That's why at a corner, the function's not differentiable, right? Because if we just very simply looked at the graph of y equals the absolute value of x, right, that is not differentiable at x equals 0 because the slope as we come in from the left, the slope of this piece here is -1, and the slope as we come in from the right, the slope of this here is a +1. So a -1 does not equal a +1. So therefore, the function is not differentiable at that corner. But notice it is continuous. All right, a derivative. We could use the limit definition of the derivative. On the AP exam, they typically give you this formula, and the goal usually is to figure out what f of x is. Whatever f of x is, you just take the derivative of it using the power rule or some simpler way to find the derivative, and that would be the answer. Okay, so the answer to this limit question is always the derivative of whatever f of x is. The power rule, I hope you know the power rule, bring down the exponent and then subtract 1 from the exponent. So that's that. The product rule is the first times the derivative of the second plus the second times the derivative of the first. The quotient rule is low. Oops, sorry. Low d high, the derivative of u, minus high u, d low, the derivative of v, all over low low. All right, so low d high minus high d low all over low low. The chain rule is when you take the derivative of the outside function first. So f is the outside function. So take the derivative of that first. And then you want to multiply by the derivative of the inside function, which is g of x in this case. All right, let me just give you a quick example of that. What if I had y equals the sine of x squared? What would its derivative be? Well, its derivative would be the derivative of the sine of something, which is the cosine of something, then times the derivative of the inside, times the derivative of x squared, which would be 2x. So that's an example of the chain rule. These trig derivatives, the derivative of the sine is the cosine, the derivative of the cosine is negative sine, the derivative of the tangent, secant squared, the derivative of the cotangent is negative cosecant squared, so I kind of usually group those two guys together. And then the derivative of the secant is secant x tan x, and the derivative of the cosecant is negative cosecant x cotangent x. Remember, whenever you take the derivative of a trig function that begins with the letter c, it's always negative. All right, so the derivative of the cosine, cotangent, and cosecant are all negative. Implicit derivatives, this is when you do not have an equation solved for y. You have x's and y's in an equation. So this one is x squared plus y squared equals 25. Take the derivative of x squared, it's 2x. Take the derivative of y squared, it's 2y times dy over dx. Whenever you take the derivative of a y, take it like you normally would using the power rule, right? That's where the 2y comes in. Bring the exponent down in front. Subtract 1 from the exponent. But then you want to multiply by dy over dx. All right, and of course the derivative of 25 is 0. And then we just solve this equation, 2x plus 2y dy over dx equals 0. We solve it for dy over dx. Okay, so that would be our derivative. If you wanted the second derivative now, you would take the derivative of the first derivative using the quotient rule, low d high minus high d low all over low low. And you want to write the second derivative in terms of x's and y's. So you just want to go back up and get negative x over y and represent that in place of dy over dx. All right, tangent lines. To write a tangent line, you need a point. So a point would be some x1 comma y1. And you need the slope. The slope, of course, is going to be the derivative. Okay, so the way we write tangent lines is using the point slope form for the equation of a line. Y minus y1 equals m times x minus x1. Of course, y and x would stay, but x1 would be replaced with that number, y1 with that number, and m, of course, with whatever the derivative was. A normal line, let me just erase that. A normal line is the same exact thing as a tangent line, but its slope is the negative reciprocal of the tangent. The mean value theorem for derivatives. The mean value theorem for derivatives basically compares the average rate of change of a function, or the slope of a secant, or the slope of a line containing the endpoints. It compares that, the slope of the secant, the average rate of change, with the slope of the instantaneous rate of change, with the slope of a curve at a single point with the derivative. All right, so the mean value theorem for derivatives sets those two equal to each other. And by doing that, you're able to figure out where the average rate of change equals the instantaneous rate of change at what x value. To find max and mins, you usually set the first derivative equal to 0. All right. You want to also look and see where the first derivative might be undefined, because we might have a corner or a cusp, and that would give us a max or a min. And you also want to look at endpoints. Don't forget about endpoints. Look, here's a function. Where's its max? Well, its max is at an endpoint. Where's the min? Its min is at an endpoint. All right, make sure that on the free response, you're justifying your answer and you're explaining. You can't just say, oh, we've got a max at x equals 4. You know, show why using a chart, using the second derivative, whatever the case may be, and then explain your reasoning. You know, there's a max at x equals 4 because the first derivative is positive, and then it is negative at x equals 4. Right, so if the function is increasing, has a positive derivative before x equals 4, and then decreasing after x equals 4 has a negative derivative, then obviously we have a maximum at x equals 4. Of course, the function is increasing when its derivative is positive. And for all these explanations, you always want to try to use calculus stuff. All right, why do we have a maximum? Well, why is the function increasing? Because its derivative is positive. Don't say because the function's going up. Why is the function decreasing? Because its derivative is negative. Points of inflection. To find points of inflection, we do the same thing with the max or min, but we set the second derivative equal to 0, and we look to see where the second derivative is undefined. We don't look at endpoints for the second derivative because you cannot have a point of inflection at the second derivative. What's the second derivative test? It's just a chart determining the sign of the second derivative. So if you determine that the sign of the second derivative is positive, then the function's concave up. If you determine that the sign of the second derivative is negative, then the function would be concave down. And you only have a point of inflection when concavity changes. Okay, you only have a point of inflection when the second derivative changes signs, not necessarily when the second derivative equals 0. These are just possible points of inflection. All right, you have to confirm that it's a point of inflection by confirming that the second derivative changes signs. Right? It's the same thing for max and mins. These are just critical values, where the first derivative equals 0, where the derivative is undefined, endpoints. They're critical values. They may be max or mins, they may not be max or mins. Let's talk about the position function, which is usually x of t or s of t. The first derivative, which is the velocity, v of t, and the acceleration, which is the second derivative, or a of t. A couple of tricky things that you need to be aware of is that speed increases when the velocity and acceleration have the same sign. So velocity could be negative, acceleration could also be negative. That means that the speed increases. Since the velocity is negative, the particle is going backwards. But since velocity and acceleration both have the same signs, the particle will actually be going backwards faster and faster and faster. Its speed would be increasing. And speed decreases when velocity and acceleration have different signs. U substitution, one very, very important way to integrate is using U substitution, right? So for this particular example, we would let U equal 4x squared minus 7. Take its derivative, find du, and then once we find du, we kind of look back up in the integral and think to ourselves, when I put the du in, what would that take the place of? And right now it would take the place of 8x dx. I like the x, I like the dx. I'm not a fan of the 8, so we need to get the 8 out of there. That's why I divided both sides by 8. All right, so then I would use u equals 4x squared minus 7 and 1/8 du to rewrite the integral. When I put in 1/8 du, it takes the place of x dx. When I put in u, it takes the place, whoops, sorry. When I put in u, it takes the place of 4x squared minus 7. And then, of course, I have a power of 10 that is still written there. All right, so then you integrate. Let me just make this a little bit bigger here. So we're integrating 1/8 u to the 10th du. All right, I technically pulled the 1/8 out in front, but it doesn't matter. So you'd have 1/8 times u to the 11th over 11. So that's why I've got u to the 11th over 88. And then I would substitute back for u, right? I'm going to go back up here and I'm going to put 4x squared minus 7 to the 11th power over 88. Don't forget about my plus c because I did not have the bounds. Okay, so there's your answer to the integral using u substitution. Let's come back up and look at derivative of exponential and logarithmic functions. The derivative of e to the x is e to the x. The derivative of e to the 5x is e to the 5x times the derivative of the exponent times the derivative of 5. All right, so that's what I've got going on there. The derivative of e to the u is e to the u times the derivative of u times the derivative of the exponent. The derivative of an exponential other than e to the x is to keep it, a to the u, log it, take the natural log of the derivative, take the natural log of the denominator, excuse me, and then multiply by the derivative of the exponent. So keep it, log it, derive it. Keep it, a to the u, log it, take the natural log of the base, and derive it, take the derivative of the exponent. So if I wanted the derivative of 5 to the power of x, that would be keep it, log it, derive it. The derivative of a natural log function is 1 over x. So the derivative of the natural log of x would be 1 over x. The derivative of the natural log of 5x would be 1 over 5x times the derivative of 5x. All right. The derivative of parametric functions. The derivative of a parametric is going to be the derivative of the y equation over the derivative of the x equation. I've got a specific video for parametrics if you want further details on that. A parametric is going to be stopped when dy over dt and dx over dt both equal 0. Okay, so you have to set both dy over dt equal to 0 and dx over dt equal to 0. That's going to tell you that the particle has stopped moving up or down, and that's going to tell you that the particle has stopped moving to the right or to the left. Okay, so just because the particle stops moving up or down doesn't mean that it couldn't be moving to the right or to the left. So in order for a parametric equation to be stopped, both dy over dt and dx over dt needs to equal 0. The speed of a parametric is this formula, the square root of the derivative of the x with respect to t squared plus the derivative of y with respect to t squared. I don't have it on this formula sheet, but I should. The length of a parametric curve, would be the integral of the speed with respect to t. And you're going to have t bounds of integration. So that would give you the length of a parametric curve. Related rates. There's 5 steps to finding related rates. First, you would draw a picture. All right, then you would come up with an equation that relates your variables. A lot of times this is, a ladder leaning against a wall, and then the ladder starts to fall. So this, piece increases. This is dB over dt. This increase the rate of change of the height, dh over dt with respect to time would be falling. And the rate of change of the ladder doesn't change at all, right? The ladder is going to be, however long it is, as it's falling down the wall. So you're going to draw a picture. You're going to find an equation. So in this particular case, it would be a squared plus b squared equals c squared, or b squared for the base plus h squared for the height equals L squared for the length of the ladder. And then you take that derivative implicitly. You take that derivative with respect to time. You substitute the values that they gave you. They'll probably give you some different pieces. They'll give you the base. Maybe they'll give you the rate of change of the base. Maybe they'll give you the height. And you need to figure out dH over dt. That would be step number 5. If all went well, solve for the final missing piece. If there are 2 missing pieces, maybe they're not going to tell you that the rate of change of the ladder is 0. You may have to go back up and think about that, and you may have to come up with that on your own. The derivative of inverse trig functions, you need to know 2 of them. You need to know the derivative of the inverse sine, which is 1 over the square root of 1 minus x squared. And you need to know the derivative of the tangent. The derivative of inverse tan, which is 1 over 1 plus x squared. Of course, if this is the derivative of the inverse tan of, the derivative of the inverse tan of 5x, right, if you wanted to know the derivative of that, that would be 1 over 1 plus 5x, the quantity squared, times the derivative of 5x. All right, so that's all that u is, just in case it's not an x. I guess, on one of the review sheets that I was doing, they asked for the derivative of inverse cosine. So you should know that the derivative of inverse cosine is negative 1 over the square root of 1 minus x squared. So the derivative of inverse cosine is the same as inverse sine, just with a negative in front. All right, integration. How do we integrate? Well, we talked about u substitution over here to the left. Here we'll talk about the power rule. So when we integrate, we add 1 to the exponent, divide by the new exponent, and then we add c. A little fact about integrals that you should know is if you switch the bounds, say you had, I don't know, you were integrating from 0 up to 2 of some function. If for whatever reason you wanted to flip those bounds, that's fine, you can do that. You would just have to negate the integral. The integrals of sine, cosine, secant x, tan x, secant squared, cosecant, cotan, and cosecant squared. These are all just the reverse of trig derivatives. Right? Of course, the derivative of the tangent is secant squared. The derivative of secant is secant x tan x. The derivative of cotan is negative cosecant squared. So these are all just derivatives in reverse. All right, let's take a look at formulas for the area under a curve. If you're looking to find the area under a curve or the area under the curve and above the x-axis, you just integrate the function. Sometimes they'll ask you to approximate the area under a curve. So when you do that, you want to do LRAM, RRAM, or MRAM, or the trapezoidal rule. Notice the formula for the area of a trapezoid is half the height times base 1 plus base 2. So if I could just quickly give you something here, and we wanted to come up with a trapezoid, say we've got these 2 points. So there's my trapezoid. The height of the trapezoid would be represented by the width of the interval. And then base 1 and base 2 are actually the y coordinates on the curve. So that's how we find the area of a trapezoid. Half the height happens to be the width of the interval from x equals 1 to x equals 3. The height would be 2 in that case. Times b1 plus b2. So whatever that y value is here, and added to whatever that y value is. All right, for LRAM, MRAM, and RRAM, you just put your top right corner of the rectangle on the curve for RRAM. All right, and if it was LRAM, of course, you put the top left corner of the curve on your rectangle. All right, the mean value theorem for integrals. A lot of times they'll ask on the AP exam, find the average value of the function. So to find the average value of a function, it's 1 over b minus a times the integral from a up to b of f of x dx. That will give you the average height of the function. So let's go back to this here. Say there were 1,000,000 y coordinates that you wanted to add up and then divide by the total number that you had. So that's kind of how the average value works. That's how the mean value theorem for integrals works, is it gives you the average height or the average y coordinates of the function over a particular bound, from a to b. The fundamental theorem of calculus is simply just integrating with bounds. Note that capital F of x a lot of times represents the antiderivative, or after you've integrated. The second fundamental theorem of calculus is a popular one. It's when you take the derivative of an antiderivative, and of course those guys cancel each other out. You just have to take the bound, which in this case is x, and substitute it into the function. Okay, so the bounds still have to be dealt with, but just when you take the derivative of an antiderivative, that cancels each other out, and you pretty much just simply plug in the bounds. All right, if that upper bound was, say, 3x squared, you would plug 3x squared in for t, and then you would multiply by the derivative of 3x squared at the end of the function. All right, for the second fundamental theorem of calculus, these all have to have a constant as the lower bound. All right, or else that wouldn't work, or else you would have to integrate the function and then take the derivative of the function and then plug in the bounds and subtract. When we're integrating exponential and logarithmic functions, the integral of e to the x is e to the x. The integral of e to the 7x is e to the 7x over 7. Okay, so that's just if it was e to the kx. It would be 1 over k times e to the kx. You could also do that using u substitution. When we integrate, say, 5 to the x power, that would be keep it and then divide by the natural log of the base and then add c. When we integrate 1 over x, that is the natural log of the absolute value of x. Okay, do not integrate 1 over x like that. Why? Well, because when you add 1 to the exponent and then divide by the new exponent, you're in trouble. All right, so if you're integrating x to the negative 1, integrate it as 1 over x, and that will be the natural log of the absolute value of x, right? Because the derivative of the natural log of x is 1 over x. Inverse trig integrals are just the reverse of inverse trig derivatives. The derivative of inverse sine is 1 over the square root of 1 minus x squared. The derivative of inverse tan is 1 over 1 plus x squared. Integration by parts. Let's take a quick look at integration by parts. This is another integration technique that's not too popular. It's only on the BC exam. It's not on the AB. But here you're integrating two functions that really have nothing to do with each other, x and the sine of x. I can't use u substitution here. So integration by parts tells me that if I'm integrating two things that don't have anything to do with each other, we'll call them u and dv, then the answer is u times v minus the antiderivative of v du. All right, so this example, I'm integrating x times the sine of x. I'm going to let u equal x because its derivative is dx. That's nice and easy. And I'm going to let the sine of x dx equal dv. All right, so that integral would be negative cosine, right? Because the derivative of cosine is negative sine, so the derivative of negative cosine is negative negative sine. All right, and then we would just plug it in to the formula. All right, so the integral of u times dv, remember this thing all here represents dv, and this represents u, would be u times v minus the antiderivative of v du. Of course, I could pull this negative out in front, and it would make that positive, and then I would get negative x cosine x plus, I have to integrate the cosine x, and when I integrate the cosine x, I get the sine of x, because the derivative of the sine is the cosine. And don't forget about your plus c at the end. All right, so that would be my answer for integration by parts. Okay, let's come back up to the top here and talk about separation of variables. All right, so if I've got a derivative, dy over dx equals 3x squared times y, I've got x's and y's in my derivative, I need to separate the variables. So the way to do that is to cross multiply and get all the y's and dy on one side of the equation and all the x's and dx's on the other side of the equation. All right, once you separate the variables, then you can integrate. What's the integral of 1 over y? The natural log of the absolute value of y. What's the integral of 3x squared? 3x to the third over 3. And then you could put the plus c down. And then at this point, they usually are going to want y equals. So now you have to solve it for y, and you have to figure out what plus c is. So I solved for y first. It doesn't matter what order you do this in, but I solved for y first by e'ing both sides up. All right, so e to the natural log of y, e's and natural logs cancel each other out. And I've got e raised to the x to the third plus c power. All right, whenever you have exponents that are added, you are multiplying with the same base. All right, and then e to a power of c is just some constant, right? 2.7 raised to some constant is just a constant, so I wrote that as c sub 1. It's certainly different from this constant up here. It's a different number, so that's why I wrote c sub 1. And then I found c by plugging in my initial values. So whatever they gave me here for x and for y, they gave me x equals 0 and y equals 2, so I plug those in. I figure out what my c value is, and I put that back into the equation. So now I've got y equals. All right, so separation of variables. We use that when we are trying to integrate something that has both x's and y's. Slope fields. A lot of times they'll give you the slope field, and you'll need to figure out which derivative it matches up with. So a lot of times what I do is I pick a point in one of the 4 quadrants, I approximate the slope of that point, and then I go through the choices and figure out, what choices have a slope that is close to what my approximation is. If I can't narrow it down after one choice, I go to usually a different quadrant. I'll go, to the second quadrant or the third quadrant or the fourth quadrant. I'll go to different quadrants. So at most, I would pick 4 points in the 4 quadrants, approximate those slopes, and then figure out which derivative matches up with my slope that I approximated. All right, so for just a quick example for, let's say, that the slope field looks something like this, and, at the point 3, 3, it looked like I had a slope that equaled +1. So that's my approximation. I go through the 5 choices, say 2 of the 5 choices give me a negative slope. Those 2 choices would be out. Then I would go to, another quadrant and pick another point. Maybe in quadrant 2, I would have, I don't know, something that looks like a 0 slope. And I would then take those remaining 3 choices and figure out which one had a 0 slope. Maybe if one of them had a slope of like 1/10, I would still keep that alive, because who knows, maybe it's not quite 0, or maybe it's a tiny bit. But if I got like -2 or 27 or something like that, then those would be eliminated. All right, the area between curves, I've got a special video on this, but the area between the curves is basically you're going to integrate top curve minus bottom curve. Everything is going to be in terms of x's. If you can't do top curve minus bottom curve, which is very rare on the AP exam, but it could happen, then you're going to integrate right curve minus left curve. And these will all be in terms of y's. Your integral will be in terms of y's. You'll have a dy, and you'll have bounds that are y bounds of integration. All right. A lot of times, again, this is rare in the AP exam, but a lot of times, they'll set that up for you by doing something like that. Here's a curve x equals, so you kind of know when you're going to write the integral, that you're going to have y's in the integral. Volume, let's talk about volume, the disk method. Again, I've got a separate video on volume, so I'll just zip through this real quickly because we could spend a half hour on this. There's the disk method, which is one way to find the volume of a function. And you're going to do that when the entire curve touches the line of revolution. Okay, that's going to be then a disk. And you're going to want to find the area of the cross section, which would be pi r squared. Figure out what the radius is, which, since it starts at the x-axis and goes up, is going to be some y value. You want to replace that y value with x's, because we're going to be integrating with respect to x whenever we revolve over a horizontal line. This is when we would revolve over a vertical line, like if we revolved over the y-axis. Very quickly, if we took something and we revolved it over the y-axis, well, that would not work here. Let's try something like this. Right, if we pick this and revolved it over the y-axis, then, you're going to be adding these up. From y equals whatever to y equals whatever. We have these horizontal disks, or these horizontal cross sections, so everything is going to be in terms of y's and dy's. The washer method is a second way to figure out the volume, and that is when the entire curve does not touch the line of revolution. So you're going to have a hole in the middle here. All right, so to find the area of a washer, you're going to do pi capital R squared. Here's the big radius. It starts at the x-axis and goes up to the curve. That's going to be some y value that you're going to want to represent in terms of x's. And the small radius, which again starts at the x-axis and goes up to the curve, that would also be some y value that you want to represent in terms of x's. The method of cylindrical shells, yeah, we did an example on that in class, but it never comes up in the AP exam, so that's not something that I would worry too much about. The surface area of a cylindrical shell is 2 pi r times the height. So that's the formula that we use for the cross sections to integrate. The fourth method is the volume of known cross sections. All right, so those cross sections, they will tell you they're going to be triangles, they're going to be squares, they're going to be rectangles, whatever the case may be. You find the area of those triangles or squares or rectangles, and then you integrate that area to figure out the volume. Here are some nice trig formulas that you probably should know. Sine squared theta plus cosine squared theta equals 1, and a couple of spin-offs from that. These are some double angle formulas. The sine of 2 theta is 2 sine theta cosine theta. I've seen that come up one or twice. So these formulas you should be familiar with. The double angle formula for a cosine. You know, what sine squared x equals in terms of the double angle for the cosine. All right, so hopefully you have a pretty good background of trig. What else do we have here? The length of a curve. All right, so over here, the length of a curve is found by integrating the square root of 1 plus the derivative squared. All right, if it's parametric, then there's not 1 plus. There's no 1 plus. It's the derivative of the x equation squared plus the derivative of the y equation squared. Partial fractions. Partial fractions is when we separate the fractions and put the denominators, or the factors of the denominators, in separate fractions, and we try to rewrite the numerators in terms of numbers. So in this case here, we would multiply top and bottom by x plus 4. Over here, we would multiply by 3x plus 5 and 3x plus 5. And then we would set the numerators equal to each other, set the x's equal to each other, set the numbers equal to each other, which would give us 2 equations. And then we would solve those equations simultaneously to figure out what A was and what B was. And once we found what A and B was, we would come back to this piece right here, and then we would integrate them separately. Integrate this with respect to x with that as a number, and integrate this with respect to x with b as a number. Euler's method. Euler's method is kind of important. It seems to come up a lot. You need to start with an initial x value, an initial y value, and some initial slope. They usually give you a formula for the derivative. The derivative equals x squared plus y. So whatever your x coordinate is, you plug in. Whatever your y coordinate is, you plug in, and you get the slope at that particular point. To get a new x value, you take your previous x value and add h. H is going to be the change in x. Right, that's going to be some change in x. They're going to have to give that to you. So to get your new x value, you take your previous x value and add h. To get your new y, you take your previous y and add h times the previous slope. All right, so that's whatever that previous slope is. And then to get your new slope, again, you go back to your derivative equation, and whatever your new x is, you plug in. Whatever your new y is, you plug in, and there you go. You have your new slope. All right, so that's Euler's method. You should know, Euler's method, you're using derivatives to approximate a function. So let's just say that this function that you were, say they gave you an initial point, I don't know, say this was the point 1,3, and they wanted to approximate the value at 2. You're using tangent lines, right? You're using derivatives to approximate that function. So if you use Euler's method to approximate the value of a function at 2, your approximation would be less than the actual value if the curve was concave up. Of course, if the curve was concave down and you were using tangent lines or Euler's method or derivatives to approximate the value of a function that is concave down, then your approximation is going to be too big. All right, because a tangent line will always be above a function that's concave down. Improper integrals, I've got a couple of examples for you here. All right, so we are going to treat an improper integral as a limit. Okay, so how do we deal with limits? Well, we approach a particular y value. So watch for this example here. When I integrate 1 over x from 1 to infinity, that integrates to the natural log of the absolute value of x from 1 to infinity. When I plug in the natural log of infinity minus the natural log of 1, the natural log of 1 is 0, but the natural log of infinity goes to infinity. So we say that this integral diverges, all right, because the natural log of infinity is too big. Whoops, sorry about that. The natural log of infinity is too big, right? When you go out to infinity, that y value keeps getting bigger and bigger. So we would not be able to nail down the area under this curve, so we say that this integral diverges. You know that that's the harmonic series when we get to series, right? Compare that to this integral here, where we're integrating from 1 up to infinity of x to the negative 2 dx. So if I add 1 divided by my new exponent, I have that. And I'm plugging in infinity, 1, and subtracting. So when I plug in infinity, when I plug in 1 and subtract, this is where the limit end of things comes in, right? This value, negative 1 over infinity, is basically approaching 0. All right, so it's nothing. And we've got 1 over here, so we would say that the area under this curve is a positive 1, right? Because this is basically insignificant. So if we were integrating 1 over x squared, the area under that curve would be 1. Let me just show you real quick on the graphing calculator if I could. If I'm integrating 1 divided by x squared, all right, and I integrated from 1 up to 10, I would get 0.9. Now keep in mind I'm integrating from 1 to infinity. All right, so from 1 to 10 is 0.9. Let's see if we could open the window up a little bit. I don't know, let's go to 100. We'll go by 50s on the x scale. Graph it again. Second trace number 7 to integrate from 1 up to 100 this time. We have 0.99. So you get the idea. As we go out to infinity, we are going to approach an area under that curve of 1. So we say that the integral converges to 1. Polar curves, I've got a separate section for you on polar curves, but real quick, to find the derivative of a polar curve, you're going to take the derivative of the conversion formulas. So you're going to take the derivative of the x conversion formula to give you dx. You're going to take the derivative of the y conversion formula to give you y. That would be the product rule, right? This is the first times the derivative of the second. The derivative of sine is cosine, plus the second, which is sine, times the derivative of the first, r prime. All right, so that's the derivative or the slope of a polar curve. To find the area inside of a polar curve, you integrate the integral of 1/2 r squared d theta. The tricky things a lot of times is figuring out the bounds, figuring out, you know, what your bounds of integration are, what values of theta give you that curve. Is how you find the bounds. Again, I've got a whole video on polar if you want to take a look at that. To find the area between two polar curves, it's 1/2 times the integral of r squared minus r squared. All right, and obviously this would be, you know, the top curve minus the bottom curve, or the right curve minus the left curve, whatever the case may be. All right, be sure to find those points of intersection, because if you want the area between two polar curves, you know, you're going to want those points of intersection. Those are going to be the bounds. Once or twice I've seen them ask for the value of dr over d theta. Remember, they're going to give you some, you know, r equals equations. So dr over d theta in this case would just be the cosine of theta. And what that means is it's the rate of change of r, Remember, r is the directed distance from the origin. So it's the rate of change of your radius with respect to theta. So for example, if r prime was positive, your radius would be getting bigger, right? As you graph the curve, your r value would be getting bigger and bigger and bigger. If r prime was negative, then your radius would be getting smaller and smaller and smaller. All right. Series. Let's talk about series. Again, I've got a couple videos for you on series. But here's the Taylor series for a series centered at x equals a. All right, so that's the formula. And the formula for the Taylor series where it's centered at x equals 0, that's specifically called the Maclaurin series. Okay, there's three pieces to these series. First piece is the derivatives, the value of the function, the value of the first derivative, the value of the second derivative, the value of the third derivative. That's the first thing. The second thing are factorials. So this would actually be 0 factorial. That's defined as 1. 1 factorial, 2 factorial, 3 factorial. That's the second thing that's with the series. And then the third thing is x. All right, here would be x to the 0 power. That's why it's not there. X to the first power, x to the second power, x to the third power. So there's three things that give you the series. The values of the derivatives evaluated at the particular point in question, the exponents of x, and the factorials. All right. You really want to remember what e to the x is, or you really want to remember the Maclaurin for e to the x. You want to remember the Maclaurin for the sine of x, which are all the odd exponents and factorials. And you want to remember what the Maclaurin for the cosine of x is. All right, we'll do an example on the next screen. All right, so let's see here. This is an AP question, and it says it's multiple choice. It says if f of x equals x times the sine of 2x, which of the following is the Taylor series for f about x equals 0? Okay, so to figure out what the Taylor series is, we could do this a couple of different ways. We could actually generate out the formula, or we could figure out what the Taylor series is for the sine. Do you remember that? It's x minus x to the third over 3 factorial plus x to the fifth over 5 factorial minus x to the seventh over 7 factorial, and so on. All right, that is the Maclaurin for the sine. All right, so if I then try to write the sine of 2x, all I would be doing is taking 2x and plugging it in wherever I saw an x. So to write the Maclaurin for the sine of 2x, 2x minus 2x to the third over 3 factorial plus 2x to the fifth over 5 factorial minus 2x to the seventh over 7 factorial, and so on. And now to finally get this red series, all I would have to do is multiply this series by x. All right, so f of x, which equals x times the sine of 2x, has a Maclaurin polynomial that's equal to x times 2x minus 2x to the third over 3 factorial plus 2x to the fifth over 5 factorial, and so on. All right, so my final answer here, I guess, would be 2x squared minus 8x to the fourth over 3 factorial, right? 2 to the third is 8. This is x to the third, and I'm multiplying by another x. It's where I got x to the fourth from. 2 to the fifth is 32. This would be x to the fifth, but I got to multiply by another one. So I've got x to the sixth, 32x to the sixth over 5 factorial, and so on. All right, this was a multiple choice question, so that would be one of the choices. All right, so let's go back and let's talk a little bit more about series in terms of their convergence. A geometric series is a series where each term is related to the previous term by a common multiple. So here you see we keep multiplying by 1/2. So it's a geometric series with a ratio of 1/2. This series converges if the absolute value of r is less than 1. If it's equal to 1 or greater than 1, then the series would diverge. If the series converges, if the value of r is less than 1, then you're going to find the sum of the series by using this formula. The first term divided by 1 minus the ratio. That would give you the sum of the series. That would give you all of these terms added up to infinity. All right, so as crazy as that sounds, we could find the sum of this series that never ends. It's the first term, which is 1/2, divided by 1 minus the common ratio, which also happens to be 1/2. All right, so I guess you've got 1 there, right? 1/2 divided by 1/2 is 1. All right, the ratio tests, I've got an example that I'll get to in 1 minute. But the ratio test is evaluating the limit as n approaches infinity of n plus 1. So you're going to add 1 to any spot where you see an n, and then you're going to divide by the original function. Okay, when you evaluate that limit, if it comes out to be less than 1, then the series converges. If it comes out to be greater than 1, the series diverges. If it comes out to be equal to 1, the ratio test is inconclusive. All right, so let's go and take a quick look at an example. So we've got the series 2x to the n plus 1 power over n plus 1, and we want to determine the interval of convergence. The first thing we should do is see if it's geometric by getting a couple of terms, but the denominator is going to ruin the geometricness of this, so we could go straight to the ratio tests. So if I evaluate the limit as n approaches infinity of, now wherever I see an n, I want to add 1 to it. So n plus 1 is obviously going to be to the n plus 2 power. And then on the bottom here, I've got n plus 1. And then I'm going to divide by the original or just multiply by the reciprocal. All right, so that is going to equal the limits as n approaches infinity of 2x to the n times 2x to the second. Why is that? Well, because this is n plus 2 here, right? And then whenever I multiply with the same base, I add the exponent. So you're always going to see this happen here. And you'll see it happen here as well. All right, and then we've still got an n plus 1. All right, that's that n plus 1 right there. And this is all over n plus 2 times 2x to the n times 2x to the first power. Again, when I multiply with the same base, I add the exponents. All right, and the reason why we want to do that is because 2x to the n and 2x to the n can cancel. And I've got 2x here, and I've got two 2x's up there. So this turns into the limits as n approaches infinity of 2x times n plus 1 over n plus 2. All right. So now when I evaluate that limit as n approaches infinity, it's a power battle. The powers are tied, so I go with the coefficients. What's the coefficients? 2x. So the value of my limit is 2x. In order for it to converge, remember we're looking for the interval of convergence, so in order for this series to converge, whatever I get for my limit needs to be between -1 and 1. All right, so I force 2x to be between -1 and 1. And then if I just solve for x, I get -1/2 is less than x is less than +1/2. Now for the ratio test, you must test the endpoints. Okay, and I need to test the endpoints because the ratio test is inconclusive at the endpoints. The ratio test is inconclusive at p equals 1, or at whatever you got for the limit, whatever answer you got for the limit. If that equals 1, it would be inconclusive. All right, so I want to test x equals -1/2. So to test x equals -1/2, I'm going to go back to that original series, and I'm simply going to put -1/2 in for x. Okay, so if I put -1/2 in for x up there, what do I have? Well, I've got a series where I've got -1, right? Because 2 times -1/2 is -1 to the n plus 1 over n plus 1. All right, so if I evaluate that, when n is 0, I get a -1. When n is 1, I get a +1/2, and so on. All right, so this obviously converges by the alternating series tests, or it's an alternating harmonic series, but we know that it converges. Okay, so we can include -1/2 in our answer. Let's test +1/2. Okay, so again, I'm going to go back to that original series, and wherever there's an x, I'm going to put a 1/2. So 2 times 1/2 is 1 to the n plus 1 over n plus 1. And let's see, when n equals 0, I get 1 plus 1/2 plus 1, plus 1/3, and so on. This is obviously the harmonic series, and it diverges. All right, so here's my interval of convergence from -1/2 to +1/2. I include -1/2. I do not include +1/2. All right, so just back to this quickly, the alternating series test. A series is going to converge if the terms alternate, plus minus, plus minus, if the absolute value of the terms gets smaller, and if the absolute value of the terms go to 0. So that's an easy test to use. The integral test is something that we really don't use, but it proves the harmonic series for us. If the integral converges, the series converges. If the integral diverges, the series diverges. The harmonic series is an important one to remember. It diverges. The alternating harmonic series is an important one to remember. It converges. The comparison test is something, again, that we don't use that much, but you can compare a series that they give you to a series that you know diverges, or maybe a series that you know converges, like a geometric with a ratio of 1/2. The p-series test is another one that's not too popular, but this p, whatever that value is, whatever that exponent is, and p is an exponent that's in the denominator, it's kind of a spin-off of the harmonic series as well, where you have exponents in the denominator. And if that exponent is greater than 1, the series is going to converge. If it equals 1, it's the harmonic series, so of course it diverges. And if it's less than 1, it would also diverge because it would wind up being bigger than the harmonic series. All right, so those are the examples we did. And then, you know, this is just some odds and ends, remainder or error. Whenever you're trying to find the error, you always go to the next term in the series that you didn't use for your approximation, and that will give you the maximum error. Okay, so you evaluate the next derivative that you didn't use for your approximation. You use the next factorial that you didn't use in your approximation, and you use the next exponent that you didn't use in your approximation to determine the maximum error of a function. Logistic differential equations is another thing where a lot of times we're just setting that equal to 0. Right, so if P is the population, say that there's, 500, the population's 500. The value of a, which is the limit of growth, in this case would be 500, right? Because when a is 500ths, all right, then you're basically maxing out your approximation, and 500 minus 500 is 0. And if the derivative is 0, then you've got a maximum population. So a logistic differential equation kind of looks something like this, where population is growing, and then it levels off because now there's not enough food or water to sustain the population. And the derivative of an inverse function, just in case they asked you that, that's that formula. And another limit definition of the derivative, I saw this once. This is a little spin-off of the limit as h approaches 0 of f of x plus h minus f of x all over h. All right, so I wouldn't worry too much about this last page here because it's not big topics. You should know to find the error, you go to the next term that you didn't use in the series for the approximation to figure out the maximum error. You should know how to set a logistic differential equation equal to 0. How is that derivative going to equal 0? And you should know the formula for the derivative of an inverse function and the formula for the limit definition of the derivative.